Good afternoon. I'm Sherri Goodman with the Center for Climate Security and the Wilson Center, here with Peter Davies of the Wilson Center, and we're pleased to welcome Jennifer Francis of the Woods Hole Research Center. Jennifer, thank you very much for joining us today for the demonstration exercise on a nuclear shipping incident in the Bering Strait in 2050. You are an expert on how weather and climate conditions are changing, how they're changing in the Arctic, and also how they're affecting the lower 48. What are your key takeaways from the demonstration scenario we did today?
So I thought it was a wonderful experience. It's a group of people that I have not interacted with before, and it was really interesting to hear how they think about the future and all the issues that are rolling around in their heads as they think about how an incident like this, which is probably not that unlikely to happen, could unfold and what we need to be thinking about to prepare. So in terms of my own area of interest and expertise, I think the concepts of prediction came out quite strongly, and being able to do a better job of predicting what the future holds in terms of the environmental conditions that an incident like this might encounter, what ships need to be thinking about as they go up into the Arctic, where all of a sudden they are able to, where they never could before. So we really need to, I think, step up our game in terms of prediction, and not just for weather, which we already do a pretty decent job of, I think, but also for ocean conditions. Because if we were to have an incident like this, we'd need to know where any hazardous materials that might leak or get released into the atmosphere, what's going to happen to them? Are they going to end up on shores where there are people living? How are they going to affect marine mammals and the marine ecosystem? So I think one of the ideas that came out was to invest in the future of prediction in the areas where shipping like this is likely to be much more common between now and 2050. And I would suggest that we not only step up that game in terms of weather with better observations, more high-resolution models that can capture small-scale events, like things like polar lows, which are like polar hurricanes that can form right along the ice edge or right along large temperature differences, say, between the land and the open water that we're expecting to see more of in winter especially. But also, I think we need to start talking about ocean forecasts. You know, we don't have an ocean forecast system yet, anything like the atmosphere. So it has been talked about, but the problem is we don't have the data that would be required to be analogous to what we use in the atmosphere to go into one of these models. So just like we have satellite information, and we have weather balloons, and we have people making measurements of temperature and pressure, and instruments of various sorts that all get ingested into an atmospheric model to forecast weather, we need to do the same thing for the ocean in this very complex but very important area, so that if we ever did have a spill or some release of contaminants in the ocean, we'd have a fighting chance to try to predict where it ended up.
What are the key missing links in having an ocean predictive capability?
Well, right now we really don't have anything like the regular measurements that we have in the atmosphere for weather forecasting. We don't have satellites passing overhead that can take measurements of things in the deeper ocean. We can measure things on the surface like temperature and even currents, but we have very little information about what happens below the surface. So things like how the temperature and salinity vary as you go down, how the currents change as you go down. All of those things affect how small-scale currents change and how they interact with the topography, and that in turn has a big impact on the living organisms that are there.
How are we going to get those measurements? Will they be satellite-based, drone-based, autonomous?
Not satellite and not drone. They can't do it. Autonomous vehicles could definitely help out a lot. I mean, some autonomous vehicles can be released and programmed to do a regular circuit, through different straits, or, just do a regular pattern around a region, and they can stay underwater for a long time and take those measurements for a while. You can put buoys underwater that give you some of that information. It's a lot harder in the ocean, and that's why we don't have it. More expensive, too.
I know that Sail Drone and others are up there taking measurements. Does that help contribute to some of the data we need?
All data is helpful. The Arctic is still a data desert in many ways. So anything that we can get more information, especially in the wintertime when there are no people up there and it's a much harsher environment, all of that information, if it can get then transmitted into the global data network that goes into the global weather forecasting system, is going to be very helpful. But sail drones aren't going to help us too much with the ocean.
Yeah, so it's interesting. Mike Farrar from the Air Force Weather Operations and yourself both commented during the panel about the sparsity of data. But you made another comment during the panel discussion which really stood out to me. And the phrase that I wrote down when you made the comment was, the climatology of Arctic storms is changing. And so the puzzle that's running through my head is, it's like we can get ourselves up to a baseline understanding of what's happening, but how over a period of time can we evolve the tools and the data collection when that baseline itself is going to be constantly changing at a rate that matters for operations up there? I mean, can you say more about this, this changing climatology and how you envision we might actually tackle that problem over essentially a multi-decade period?
Yeah, so there hasn't been a lot of research on the fact that as we lose the sea ice so rapidly, it is going to have an impact on the storms that either move into the Arctic or even form in the Arctic. And as I mentioned during the panel, the Arctic used to be thought of as kind of a graveyard for storms. They'd come up from the Pacific Ocean and they'd basically die over the ice, or they'd come in from the Atlantic and they'd basically die over the ice. But now that the ice is so diminished, we have all this open water that really transmits a lot of energy into the atmosphere that the storms can ingest and either keep going rather than dying, or new storms can actually form. And one of the interesting things in the winter is that if we have this open water continuing well into the winter months, then we find these huge temperature differences between the land, which is cooling off really fast, the ocean water, which stays basically at the freezing point and can't get any colder until it freezes, and the ice that's still existing there. So these big temperature differences along these edges are fuel for storms. So by having these new edges and new big temperature differences, this is leading to this idea that the storm climatology is changing. The only way we're going to get a handle on, monitoring that change and forecasting those changes is to have higher resolution atmospheric models that get more observations into them about these they're relatively small scale changes, but that really matter for how weather systems develop. So we both talked about needing a better observation network, higher resolution observations. These are not cheap, they're not easy, but the technology does exist.
And they probably need to happen year-round, not just in
Absolutely
the seasonal
year-round.
seasons when they're easier to take.
Absolutely. And satellites can help to an extent, but if there's a lot of clouds around, then it's hard to see the surface. Infrared information doesn't penetrate clouds, and microwave information tends to be fairly large footprints. So we've got a lot of sort of basic challenges when it comes to satellite information.
Thank you. Thank you for this sort of the combination of additional insights and then explaining it in a way that's, you know, that's understandable for a broad
Happy to
cross-section of folks.
Happy to try to help.
So with that, we really want to thank you for your time, both earlier today and for spending this extra time with us. So thank you.
It was a pleasure. Thanks.
Thank you, Jennifer.